Okay, we are very pleased to have Rankeya Datta, who is between the University of Illinois in Chicago and Michigan State University, who will tell us about splinters, an introduction, and open question.
All right, thank you very much. I'd like to thank the organizers for the opportunity to speak today. So today's talk is going to be an overview of a class of singularities that was introduced last week in the lecture series on the mixed characteristic MMP from a global perspective. But today we're going to look at this class of singularities from a local perspective, but they have a different name, namely a splinter. So even before I begin my talk, I apologize because I'm going to use this different terminology today, but I hope that it does not cause any confusion, because one is a global notion that was studied last week, and today I'm going to study the local aspect of these singularities. And today's talk is partially based on joint work with Kevin Tucker. All right. So my simplifying assumption throughout is that R is going to denote a Noetherian integral domain. I don't really need things to be integral domains. And the first definition that I make is going to be valid even for non-Noetherian rings. But let's make this simplifying assumption. And like many things in commutative algebra, my talk today is going to begin with a theorem by Mel Hochster from 1973. So Hochster showed that if R is a regular ring that contains a field, so we say that R is equal characteristic. So then he showed that any finite extension from R to S is going to split as R modules. So what this means is that it admits an R linear left inverse. So what I'm going to do is I'm going to call this splitting condition the property that finite extension split as star with the blue color. All right, so this is a statement about equal characteristic regular rings. So now it's natural to conjecture that it holds indeed for all regular rings. And that is precisely the famous direct Summand conjecture, which was finally proved by Andrei in 2016. And so the direct Summand conjecture is that regular rings in mixed characteristic satisfy the splitting condition star. It's hard to do justice to the importance of the direct Summand, to the importance of the direct Summand conjecture in like a couple of minutes, but I will say that the direct Summand conjecture has been shown to be equivalent to many statements in homological commutative algebra. The statements don't seem like they have anything to do with the direct Summand conjecture, but turn out to be equivalent to it. So for example, one of my favorite such statements is this conjecture by Renaud Grousseau, whose slogan is that flatness descends over integral maps. And I'm not going to write it down because it's not relevant for my talk today, but the conjecture states that suppose you have an integral extension from R to S, where say the base ring R is Noetherian, and suppose you have a module M over the base ring R. If the extension of scalars of M to S is flat as an S module, then it must be flat as an R module to begin with. So this statement about descent of flatness turns out to be equivalent to the direct Summand conjecture. And there are many other such non-obvious statements that turn out to be equivalent to it. So that's all I'm going to say about the importance of the direct Summand conjecture today. But so now that we know that regular rings satisfy the splitting condition, it's very natural to study the class of rings that satisfy the splitting condition. And so this was the definition that was first given by Frank Ma in 1988, and it's going to be that of a splinter. So a ring R, which is not necessarily regular, is going to be called a splinter if it satisfies the splitting condition star. So if every finite extension with R as the base splits. And so the upshot of the direct sum and conjecture is that because regular rings satisfy the splitting condition, the splinters form a characteristic independent notion of singularity. So splinters are a characteristic independent notion of singularity. But it took until 2016 to actually be able to even justifiably call them a notion of singularity, right? Because we didn't know if regular rings were splinters before that in general. Okay, so I'm going to make a couple of remarks now. And the first remark is going to be about what I said at the beginning of today's talk, is that the definition of splinters globalize in a very natural way. You can replace R by a scheme and replace finite maps, affine maps by finite global maps and so on. So the definition globalizes, and global splinters have been recently called globally plus regular. In the mixed characteristic minimal model program. So see the talks from last week. But I'm going to be calling this class of singularity splinters today. And again, I hope that this does not cause any confusion, because I'm not going to be concentrating on the global picture much today. Also, the second remark I want to make is that there is a derived analog of this notion of splinters where you replace finite maps by proper surjective ones. And this gives rise to a notion called derived splinters. I'm not going to formally define derived splinters, and the reason for that is the following. So Bhargav in 2010, in his thesis, and more recently forthcoming work of Bhatt and Lurie, is going to show that derived splinters are actually equivalent to splinters under very mild conditions in prime and mixed characteristics. And as I will discuss shortly, the notion of a splinter is not very interesting in equal characteristic zero. But in all other characteristics, they're the same as their derived counterparts. And so I'm not going to differentiate between derived splinters and splinters today. And so Bhargav also improved on Andre's result from 2016 and showed that regular rings, in fact, satisfy the stronger condition of being a derived splinter. But this does not directly follow from the forthcoming work of Bhatt Lurie, because chronologically, regular rings being derived splinters came before this forthcoming result. Okay, so as I was saying, the notion of a splinter is not very interesting in characteristic zero. So in characteristic zero, splinters, and when I say characteristic zero, I mean it contains the rational numbers. The ring contains the rationals. So splinters are equivalent to being normal. And the way you can construct splittings is via field trace, normalized field trace maps. So you take the trace of a finite extension of fields, and then you divide it by the degree of the extension. That gives you a map from the bigger field back to the smaller field, and you can restrict this map to get splittings at the level of finite extensions. So splinters are the same as being normal in characteristic zero, so they're not very interesting. But what is interesting is that this derived notion of a splinter, even though it's equivalent to splinters in prime and mixed characteristics, actually is very different in equal characteristic zero. So Kovacs proved that if R is a finite type over a field of characteristic zero, then R is a derived splinter. If and only if R has rational singularities. Oops. So in particular, derived splinters and equal characteristic 0 are Cohen-Macaulay, whereas splinters are just normal, so they need not be Cohen-Macaulay in equal characteristic 0. So these two notions diverge in equal characteristic 0, but coincide in prime and mixed characteristics. Are there any questions so far? Okay, so the fourth remark I want to make is in the local setting. So suppose you have a local ring, excellent local ring, which is a splinter and which is of prime or mixed characteristic, then R satisfies the following additional nice properties. So the first thing is, and this is true for all splinters, R is normal. But in prime and mixed characteristics, R is going to be Cohen-Macaulay, and this, I'll say a bit more about this in a second. And moreover, R is also going to be pseudo-rational. So the normal part is not hard to show, but the fact that R is Cohen-Macaulay splinters in prime and mixed characteristic are Cohen-Macaulay and pseudo-rational are non-trivial results. So in prime characteristic, this follows from the work of Smith. This is essentially Karen Smith's thesis. And in mixed characteristic, this is recent work of Bhargav Bhatt from 2020. And moreover, so not only are splinters in prime characteristic pseudo-rational, Karen Smith showed that they're in fact also F-rational, if you know what that means. Okay, so I've introduced this notion of a splinter in a Noetherian setting, but to do things with splinter, one often has to pass to non-Noetherian rings, and this might relate more to the terminology plus regular from last week. So this point is that the splinter condition can be checked via this highly non-Noetherian ring called R+. So what is R+? So where R+ is the integral closure. It's called the absolute integral closure of R. So it's the integral closure of R in an algebraic closure of the fraction field of R. So it's not canonical because algebraic closures are not canonical, but it is unique up to isomorphisms, but non-unique isomorphisms. So how does R+ detect splinters? So one can show that R is a splinter if and only if the following nice ideal contraction result holds. So if and only if for all ideals I of R, so R+ is some ring that contains R. So what you can do is you can take this ideal I, you expand it to R+, you get some bigger ideal, and then you contract back to R. And R is going to be a splinter if and only if this expansion contraction operation gives you the original ideal itself. So another way to say this is if when you tensor the injection from R to R+ by R mod I, the resulting map is injected. Okay, are there any questions about my preliminary remarks about the notion of a splinter? Okay, so then let's discuss some examples. I'll start with some silly examples. Direct Summand conjecture implies that regular rings are splinters. And as I said, normal Noetherian Q algebras are splinters. But if you want to construct more interesting examples of splinters, and they're pretty hard to construct in general. But one class of examples comes from the following very interesting observation, is that the observation is that the direct summand of splinters are splinters. So in particular, direct summands of regular rings are going to be splinters. So that's going to give you singular examples of singular rings that are splinters. So the simple observation is that if R2S is an extension that splits, and if S is a splinter, then this implies that R must also be a splinter. So in particular, if you take S to be regular, this is saying that direct summands of regular rings are splinters. So let's see some interesting classes of rings that are splinters because they're direct summands of regular things. So the first class is going to be the coordinate rings of affine toric varieties over fields. You have to think a little bit to see why they are direct summands of regular rings, but in this case, they're in fact direct summands of polynomial rings. You can use the semi-group structure to construct such a splitting. So that's one example of splinters. Here's another one of certain types of quotient singularities. So suppose K is a field, and let G be a finite group that is acting on the polynomial ring in n variables over the field K. And what I'm going to assume is that the order of this finite group does not divide the characteristic of the field K. So the order of the group is invertible in K. So that's what this means. So then the ring of invariance of this action is a splinter. And in this case, it's actually pretty easy to construct an explicit splitting. So what you have is that the Reynolds operator, the averaging operation, because now the characteristic, now the order of the group is invertible in the field. So the Reynolds operator, which is going to be the map from, so I need to construct, I need to exhibit R, the ring of invariance as a direct summand of R. So I need to construct a map from R to the ring of invariance that sends 1 to 1. That's what it means to be a direct summand. So the map from R to its ring of invariance that sends X to this average is going to give a splitting. Okay. Any questions so far?
Do you have similar results for linearly reductive groups?
Linearly reductive groups are linearly reductive actions of linearly reductive groups splinters in general. I'm not sure if there's splinters in general.
And isn't there still a Reynolds operator?
There still is, but
So as long as you're a summand of something regular.
yeah. Sorry. Okay. So another example in this class of examples is Veronese subrings of a polynomial ring of over any regular ring. So I'm calling the regular ring K, but doesn't matter. So one such specific instance of a Veronese subring is this one. Which may be more familiar to you. This ring, so this is Veronese subrings have a degree preserving splitting. So here K can be really anything. K can be a field, it can be Z, or it can be any regular ring. Because then R adjoined to the variables is all, again, regular, and then you're expressing this as a direct summand. Okay. So these are direct summands of regular rings. So now I'm going to talk about certain classes of rings that are not necessarily known to be direct summands of regular rings in prime characteristic and fail to be direct summands of regular rings in mixed characteristic. So you take a generic M by N matrix of indeterminates, and you choose an integer t that is less than or equal to the minimum of m and n. So if you let it be the ideal generated by the size t minors, of this generic matrix X, then for a field K, the quotient of this polynomial ring with these m times n variables, modulo this ideal of size t minors, is a splinter. And I've been careful to use a field here. So this is not easy to see. I'm not claiming this is easy to see. And the reason why this splinter when K has prime characteristic is because it's F regular. And F regular things are splinters. So this is really a result of Hochster and Hunekeen prime characteristic. And I'm not sure what this ring is when K has mixed characteristics. So for example, if K is integers, I'm not sure if it's known that this thing is a splinter then. But in the case where K is has mixed characteristic, this quotient ring, which is a generic determinantal ring, is known to not be a direct summand of a regular ring. In prime characteristic, I believe this is still an open question, if I'm not mistaken. So I don't know if this fourth example is really part of the previous set of examples in prime characteristic. Okay. And so my final example is going to be one that's going to use a notion that I'm not, unfortunately, going to define in today's talk. So suppose R is excellent. So, and I'm going to let this tau R go, let it denote the test ideal in characteristic P bigger than 0. And it's going to denote the big Cohen-Macaulay test ideal with respect to R plus in mixed characteristic, when R is complete local in Q Gorenstein. So all I'll say about the test ideal, this BCM test ideal and the test ideal in prime characteristic, is that it's an analog of a multiplier ideal from characteristic 0 by rational geometry. So they satisfy many of the good properties of multiplier ideals that make the latter a robust tool in birational geometry. So if you take this test ideal, and then if the test ideal is trivial, it then implies that R is a splinter. Okay. So any questions about the examples? All right, so this last example is going to lead to my first open. So I've sort of introduced splinters and given some examples. So now I'll talk about some open questions about these class of singularities. And I think the point is that the definition of a splinter is very easy and very general. And so I think it's this generality that makes it very difficult to actually prove interesting things about splinters. So that's the point, I guess, that'll come across in the rest of today's talk. So the first open question is a natural continuation of this example 5. And I'm going to state it in characteristic P. So suppose R is excellent of prime characteristic P bigger than 0. So this is a very big, important open question. So the question is, if R is a splinter, then does it follow that this test ideal is trivial? So the previous example is saying that if the test ideal is trivial, then the singularity must be a splinter. So the first big important open question is asking about the converse. If the ring is a splinter, is the test ideal trivial? And there are partial answers for this important open question. So the first partial answer is by Anurag Singh, who proved that if R is Q Gorenstein, then this is true. Characteristic P bigger than 0. And then there is a related result by Kiekio, I hope I'm pronouncing the name correctly, Enescu, Miller, Schreed, And I think there's also unpublished work of Singh that proves the same result, but it's
Rankeya, sorry. So what's your
yes.
definition of the test ideal here in non-complete case?
I was hoping to brush it under the rug, but you can take whichever definition you want. You can take the definition of it to mean a big test ideal in the F finite case, and I can also take it to mean the so there's the big test ideal and the not the small, what is it called? The non-finite, the finitistic test ideal. See, this is open for both kinds of test ideals. So the original tight closure conjecture is that if this tau of R is the non-finite, is the finitistic test ideal. And if it's a splinter, then the finitistic test ideal equals the whole ring.
But it is defined over R, or is it defined over R plus for you?
It's defined over R.
Over R of the completion.
It's defined over R.
Okay,
not
thanks.
The completion. Yeah, not the completion. Sorry, I misunderstood what you were asking. Okay. So the second affirmative result is that R has a finite Frobenius and a finitely generated anti-canonical ring. So then this conjecture is true. So these are the only two known cases in which this conjecture is true apart from low dimensional things, I think. And so the reason why this question is important will appeal more to commutative algebraists, it's because it implies a very long-standing conjecture in tight closure theory, which is namely whether weak F regularity localizes. So weak F regularity, if you know tight closure, is the property that all ideals are tightly closed, but it's not known if when all ideals are tightly closed, then the localization of such a ring has the same property. So this conjecture, if it has an affirmative answer, will imply that weak F regularity localizes. Because this condition, that tau of R equals R, is precisely the statement that the ring R is weakly F regular. That's another way to state it. Okay. So my first question uses this notion that I'm not defined, and so you might be very unhappy. So now let me reinterpret this question in a maybe more algebraic and slightly more accessible manner. So for this, I'm going to restrict to a complete local domain of prime characteristics. And so we have three types of singularities. So there's weakly F regular, which implies a splinter, which implies F split. And so how do you recognize these singularities? Well, F split is the property that the map from R to its perfection splits. Splinter is the property that the map from R to R plus splits. And I need my ring to be complete here to talk about splittings. In general, the map from R to R plus is not going to split if you're not complete, even for nice rings, like Tate algebras. Okay. And then weakly F regular is the assertion that the map from R to a ring B splits for all big Cohen-Macaulay R algebras B. This is a non-trivial equivalence. It doesn't straight away follow from the definition of weak F regularity, but it follows from work of Hoxter on solid closure that this is in fact equivalent to weak F regularity. So what is the previous, and so for those of you who do not know what BCMR algebras are, there's a definition here. So what is the first open question really asking, at least in the complete local domain case? It's asking if this implication is true. If the map from R to R plus splits, then does it imply that the map from R to any big Cohen-Macaulay algebra always splits? And R plus itself is a big Cohen-Macaulay algebra by a non-trivial result of Hoxter and Hulicki from the 90s. So yeah, so that's the first big open question. Any questions about that? Okay, so the question of leads now, well, I guess the next question that I want to state is not related to the first one. So suppose phi is a ring map from R to S, and I'm going to assume that phi satisfies certain conditions. So the first thing is that phi is flat. And the second condition is that R and S are both Noetherian. Everything is Noetherian for me in this talk, apart from R plus, which is not. And that the fibers of phi are geometrically regular. So this is my assumption on the map phi. And this kind of a map is usually called a regular map in the literature. So phi is regular if it satisfies these three properties. It's flat, both the base and the overrings are Noetherian, and the fibers are geometrically regular. So then the next question is whether the property of being a splinter passes from R to the ring S. So the question is, if R is a splinter, then does this imply that S is a splinter? Is S also a splinter? And I guess the reason why this is a somewhat reasonable question is that so splinters form a class of singularities, and other notions of singularities are known to ascend at the regular maps. So notions such as reduced, normal, Cohen-Macaulay, Gorenstein, complete intersection, most notions of F singularities, if you're familiar with them, and more recently, pseudo-rationality in characteristic zero, and rational singularities for finite type things over fields before that, but are known to ascend under regular maps. But we do not know this about splinters.
Not even for joining a variable or a power series variable?
You are predicting where I'm headed, so stealing my punchline. All right, so if you've never thought about regular maps before, let me give you some examples of regular maps. So the first example is that if you have an excellent local ring, again, it doesn't matter if you don't know what an excellent ring is, most rings are excellent. If you have an excellent local ring, then the map from this ring to its M-adic completion satisfies the conditions of being a regular map. So that's the first and one of the most important examples of regular maps. Étale maps are regular. And more generally, smooth maps are regular. Okay, so it's an open question whether the property of being a splinter ascends under regular maps, but Kevin and I do have some partial results in this direction. And the partial result that we have is that the splinter property ascends if your map is the completion map and if it's étale. Ascends in cases 1 and 2. Okay. And what I want to say is that this case 3 of the map being smooth, and when I say smooth, I'm assuming everything, the map is of finite type. Okay. So the case 3 is actually not much more general than the case of an arbitrary regular map because of Néron-Popescu desingularization. But before I say that, I just wanted to say that nothing is known about the smooth case, apart from the instances where splinters are already known to coincide with other notions of singularities. For example, in the Q-Gorenstein setting. So 3 is wide open in prime and mixed characteristics. And you might be curious to know if completions of splinters are not always splinters, because completion of a Cohen-Macaulay ring And a Gorenstein ring turns out to be Cohen-Macaulay and Gorenstein as well. But it is true that there are examples. So completion of a local splinter is not necessarily a splinter in general. So you do need some control on the fibers, the formal fibers. Okay, so now what I want to say is that the case of a smooth map is not much more special than the case of regular maps in general because of Néron-Popescu desingularization, which states that if you have any regular map, so a flat map where both rings are Noetherian and where the fibers are geometrically regular, then you can express this as a filtered colimit of smooth maps. So every regular map is built out of smooth maps. And if you're familiar with smooth maps, then you know that smooth maps themselves factor locally as polynomial extensions followed by étale extensions. So what does this mean for us? This means that this question 2, which was whether the splinter property ascends under regular maps, thanks to this theorem in the étale case, reduces to the following very simple sounding question, which Carl anticipated. So the question 2, the revised question 2 is question 2 prime. And I find it very shocking that this is an open question, but the question is, if R is a splinter, then your joiner variable doesn't remain a splinter. No one has any idea. Now, this question might sound simple, but what I want to emphasize is that it's likely difficult. And it's likely difficult because it implies the direct Summand theorem. So the direct Summand theorem is actually now a special case of this simple sounding question. And the direct Summand theorem, at least in mixed characteristics, does not have a proof that's completely straightforward. So this is also likely a difficult result. But what's surprising here is that this question is wide open even in prime characteristic, where usually things are easier to prove. So this question is even open for finite type rings over fields in prime characteristic. In characteristic 0, this question is a non-question because R is then normal, and you know that when you join a variable to a normal ring, it stays normal. But it is an open question in prime and mixed characteristics. I think there is no one has any idea what happens in mixed characteristic. And in prime characteristic, this is known in the Q-Gorenstein case, because you know what splinters are equivalent to other types of singularities. And so you can work with those other singularities instead. Okay, so that was my second open question from today's list of open questions. Any question? All right, so then I'm going to move to another question that is related to this ascent under regular maps type of problem. So I'm going to assume that R is an excellent domain. And so the question is the locus of points where the local ring is a splinter? So you can look at this set that I'll call SPL of R. So is this open? So is the splinter locus of an excellent ring open? i.e., what is this saying? This is saying, can we spread out the splinter property from a point to an open neighborhood? So that's my third open question. And it's related to the second open question about ascent under regular maps, because you can often use those kinds of results to show openness of loci. So I want to make a couple of remarks about this question. The first is that splinters are normal. So the splinter locus is always contained in the normal locus. And the normal locus is known to be open when you're excellent. This is in the EGA, for instance. But now you might be wondering, well, is the splinter, do we really need excellence to show openness of splinter locus or to ask this question? And there's this ridiculous construction by Mel Hochster who shows that most properties, local properties of Noetherian rings will not have open loci if you enlarge the class of rings to include ones that are locally excellent, but not necessarily excellent. And when I say locally excellent, I mean all the localizations, all the stocks are excellent. So Hochster showed that there exists a Noetherian domain A such that for all prime ideals P, this localization, he localized that P is essentially a finite type over some field. And what's funny is that this field is going to depend on the prime P. It's not essentially a finite type over a fixed field. So as you vary the points P, the resulting rings that you're going to get are all going to be essentially a finite type, but over different fields. Fields depend on P. So it is something that's locally excellent. It's locally a very nice ring that we all like and love, but the splinter locus is not open. In fact, most singularities will have non-open loci using these types of examples. So this is an example of a ring that's locally excellent, but is not excellent globally. So I really want to restrict myself to the class of excellent domains for this openness of loci question, because it's false even for nice but pathological rings outside the excellent setting. And I guess the third remark I want to make is that the splinter property, and I did not mention this for whatever reason before, but the splinter property can be checked locally, unlike some other notions of F singularities like weak F regularity. So R is a splinter if and only if this set SPL of R is all of R. So a ring is a splinter if and only if all its local rings are splinters. And again, question 3 is reasonable because other local properties often have open loci for excellent rings and schemes. For example, Cohen-Macaulay locus is open, normal locus is open, Gorenstein locus is open, complete intersection locus is open, and so on and so forth. So this is a reasonable question. So we have some partial results toward this question, Kevin and I, in positive characteristic. Yeah, none of our results seem to generalize to mixed characteristic. But so the setting is let R be an Noetherian ring of prime characteristic P bigger than 0. So then we show that the splinter locus is open in each of the following cases. So the first case is when the Frobenius on R is a finite map. So this includes, in particular, all varieties over perfect fields of prime characteristic. So then the splinter locus is open. Next, we show that the splinter locus is, we can show it for certain types of non-F finite rings. So for example, if R is essentially a finite type, over an excellent local ring. So for example, if you're essentially a finite type over a complete local ring of prime characteristic, then this locus is open.
So sorry, essentially finite type just means a localization of finite type, right?
That's correct, yes, localization of finite type. And the third case is, is not very interesting, but I just don't know if it's actually an additional case or if it's subsumed by the previous two cases. So if you're local in Frobenius split, then this locus is also open. Okay. So these are the three cases where we know that the splinter locus is open, and they're all in positive prime characteristic. Okay, so question 3 is wide open in mixed characteristic and for arbitrary excellent rings in prime and mixed characteristic. So this does not cover, these two cases do not cover the class of all excellent rings. F finite rings are excellent. This is the result of Kuhn's. And I'm taking something essentially a finite type over excellent, so that's also excellent. But there are excellent rings that are not F finite and not essentially a finite type over excellent local. Whether they're interesting to you is for you to decide, but yeah. So these are the settings in which question 3 is open. And so as a fun application of this previous result, we were able to show the following result about graded rings that was surprisingly also open. So let K be a field. And suppose R is a ring that's graded by the positive or non-negative integers, such that the degree 0 graded piece is the field K itself. So let M be the homogeneous maximal ideal of R. So what we can show using this openness of loci and the ascent of the splinter property under étal maps is that the homogeneous maximal ideal of a graded ring over a field can detect the splinter property. So R is a splinter if and only if its localization at the irrelevant ideal is a splinter. That's one fun application of this openness of loci question. But perhaps what's more important in this openness of loci question is the following stabilization result, which is similar to some stabilization results that were stated last week, similar in spirit. Okay, so the setting is as follows. So again, everything is in prime characteristic. So let R be a Noetherian domain of characteristic P bigger than 0 that satisfies either of the following two conditions. The first condition is that R is F finite, which again means that the Frobenius map on R is finite. And the second condition is that R is essentially a finite type over an excellent local ring of prime characteristic. What we're going to do next is we're going to fix an absolute integral closure of R plus. And so then we have the following stabilization result. So if the Frobenius map on R is universally injective, which just means that whenever you tensor this map by any R module, it stays injective. You might also know this as R being called F pure. So if R is F pure, which is a necessary condition in order for R to be a splinter in prime characteristic. So if R is F pure, then the following infinite intersection ideal, and I'm going to denote T sub R. So what's this intersection going to be? It's going to be the intersection over all finite sub-extensions of R plus. And what I'm going to do is I'm going to take the intersection of the following ideals. So I'm going to look at the canonical map from the dual of S, R dual of S back into R. And what is this canonical map? This is evaluation at 1. So these images are going to give me ideals, and I'm going to let S vary over this set of finite sub-extensions of R plus. And I'm going to take the intersection of all of these images. And so what we prove is that this infinite intersection stabilizes. And what do I mean by that? So i.e., what I mean by this is that there exists an R subalgebra. Let's call it S naught, contained inside the absolute integral closure R plus, such that first, I can choose this extension. So it's going to be finite, but moreover, I can choose it to be generically étal. So the induced map on fraction fields is separable, finite separable. And second, this ideal TR that I've written is an infinite intersection of these images of evaluations at one maps. But what we prove is that when R satisfies the two conditions 1 or 2, and when the Frobenius map is pure, then this infinite intersection is actually collapses to one of these images for some S naught. We don't know what this S naught is, but there exists an S naught, such that this infinite intersection becomes the image of the evaluation at one map for one finite generically étale extension. Okay, so let's wrap our head around this intersection. I said that a ring is a splinter if every finite extension splits. Splitting means that you have a map from the overring to the base ring that sends 1 to 1. So this will tell me that a ring is a splinter if and only if this infinite intersection ideal T sub R is trivial, if and only if it's the whole ring, right? So R is a splinter if and only if T sub R is the whole ring. So what's the upshot of the previous stabilization result? So splinters, as defined originally, is something that you need to check for infinitely many finite extensions. You have to check splittings for infinitely many finite extensions, or you need to work with the big ring R plus and prove properties about the map from R to R plus. But what this stabilization result is saying is that for large classes of excellent F-pure domains R, the splitting of a single appropriately, I guess, I couldn't really phrase this well, appropriately chosen generically étale finite extension determines whether the original ring is a splinter. So a definition that a priori relies on checking the splitting of every finite extension reduces to checking whether one particular finite extension splits. But the point here is that there is no good control over what this finite extension should be. But there is such a stabilization result. And we use this stabilization result to work with ideals that define the non-splinter locus of the ring R to show that it's open. So then I want to, I guess I have 7 more minutes. I want to end with a few questions. So the first question is that or rather Kevin and I proved this result for excellent F-pure domains, the stabilization result for excellent F-pure domains. So the natural question is, does the previous stabilization result hold for arbitrary excellent F-pure rings or F-pure domains, rather? And then the second natural question that you may have is what happens for non-F-pure domains? I don't know if the stabilization fails. It likely fails, but I'm not sure.
Do you know?
Carl, do you know this?
I mean, in the F-finite case, in the Q Gorenstein or finite generated anti-canonical, that stabilization holds. I don't know. I mean, are you able to prove that the maybe someone else here, Lingshuan or Kevin, can say, do we know the stabilization holds in the F-pure case, or sorry, in the F-finite case?
In the non-F-pure setting?
Yeah. Under Gorenstein type hypotheses, Q Gorenstein?
I do not know. So I'll be happy to
the local
know the
case
answer.
is probably the local
Okay.
case. Okay.
Okay. So then I guess.
Sorry, in that
naturally,
in the Q Gorenstein case, is there like an sort of a way to say what this algebra is, this S, or is it just something that comes out of the proof?
It's just a consequence of the equation lemma and the dualities, like in the Huneke-Lubeznik paper.
And so I guess this was all in prime characteristics. So you can naturally ask, are there analogous stabilization results in mixed characteristic? I don't know if anything is known. Outside Q Gorenstein settings, this maybe. Okay, so that was what I had prepared, but I had 4 more minutes. So now I guess I can end with 2 questions that I have no progress on whatsoever.
So may I have a question?
Yes.
What about the global case? Do you say, can you say anything about, say, globally like F splits, projective varieties?
I mean, under Q Gorenstein hypotheses, everything's fine. Outside of Q Gorenstein hypotheses, I bet almost nothing's known.
Okay.
In the F finite case again, I'm probably assuming secretly.
Yeah.
But then I was talking about the globally F splits case, right?
Yeah, in the F finite case, if under Q Gorenstein hypotheses, I think everything's fine.
Okay.
Outside the F finite or Q Gorenstein case, I bet we know almost nothing unless Rankeya knows how to do it.
So Jakub, I think to address some of your questions, so what we use is this notion of uniformly F compatible ideals, right? And they are known to be finite in number under F split and F finite hypothesis. And yeah, so we need kind of those the F compatible ideals to be finite in number. So I don't know what happens outside the F split setting, because they are certainly not finite in number outside the F split setting. They're uniformly F compatible ideals. Okay, so 2 minutes. Okay, I should end my talk here. Sorry. Yeah, let me end my talk here.
Okay, I'll ask a question. What was the question you were going to ask?
So the questions there were 2 questions. They were about some global stuff. So the first question, open question 5, was suppose let X be projective over a complete focal ring R, and let L be an ample line bundle on X. So then the question, I think this is open, is that if X is globally plus regular, is the section ring actually a splinter?
Is this asking, is a graded splinter the same as a splinter? Secretly?
I'm going to get to that next.
Okay.
That was my next question. Question 6. So suppose you have an n-graded ring, Noetherian domain, and then you can take the graded analog of an absolute integral closure, which I don't want to define because I get confused every time with indices. So there is a graded analog of the absolute integral closure, and then you can ask if the map from R to the graded analog of the absolute integral closure is pure, then does this imply that R is a splinter?
Bargov, didn't you prove some things about like there are certain classes you can kill with homogeneous things or can't kill with homogeneous things, but can kill with non-homogeneous things? Aren't there some results like that? Or did you? Maybe it wasn't you.
Sorry, I think there was some result that so Sanai and Singh have this separable thing where you can use separable extensions to kill local cohomology classes in the affine case, and then I think it was true that in the projective case, maybe separable is not enough. But that's the only thing I can think of.
Okay. Okay.
Anyway, these were the list of questions I had. Likely more important, like other important questions as well, but I haven't been thinking about them, so they're not in the list.
All right, well, let's thank Rankeya. Are there any more questions? I was going to ask question 6. There's a question in the chat. I don't know if you see it, Rankeya.
Yes, is it possible to outline the main obstruction for deducing R? Okay, so the main obstruction to deducing R is a splinter. If R is a splinter, is R adjoined X a splinter? So the obstruction that I can see is the following. So R is a splinter, means that the map from R to R plus is pure. To show that R adjoint X is a splinter, you need to show that this map is pure. This map is going to have a natural factorization. This first map is pure by base change because R to R plus is pure. The thing that I don't seem to be able to understand is this, what this thing is. This is an extension of non-Noetherian rings. And I don't know what, if this map were pure, then we would win. But I don't know what's happening with this map. Is one obstruction that I am facing. Okay.
Maybe a quick comment. I bet 5 and 6 are okay if you assume the graded ring or section ring is Gorenstein.
I see.
Just because everything's the same as tight closure type things. Any more questions? All right, if not, let's thank Rankeya again. And just a reminder, tomorrow after the talk, we do have a poster session. So, you know, hopefully you can all join us.
Thanks, Carl.